All right, so this is module 2 of our workshop. And just as a review of where we're at, so we already covered our introduction to digital twins in Industry 4.0. We're going to start with the introduction to simulation and Simio coming up next. And as a reminder, this one and the next 3 modules will be an opportunity to have hands-on software. So if you don't have Simio installed, you can go to the website that is here and download it, or you can go to your workshop pre-work and get at it. And so this is the section we're going to talk about now, Introduction to Simulation and Simio. So we're going to talk a little bit about simulation generically, so that we get all on the same page as what we're talking about with simulation. And then we'll illustrate that with an introduction to Simio. Okay, so to go forward, what exactly is simulation? Well, our goal is to mimic behavior over time of a real system with a model that behaves in a similar way. What are some applications you might encounter in your daily life? Normally in a live group, I'll look for a show of hands of how many people have used simulation today, and usually I get almost none. But when I ask for how many people have looked at the weather forecast, today, a lot of people say, "Oh yeah, I looked at that." Well, that's based on a simulation. How many people played a computer game like Minecraft or Fortnite or something like that? Yeah. How many people flew on a plane recently? Well, flight simulators are used for pilot training. So, there are lots of common uses of simulation. The models that we're talking about are generally purpose-built to answer a specific question. So when I highlighted that model behaves in a similar way. Well, how similar is similar? Well, there's a famous quote from George Box that says, "All models are wrong, but some models are useful." If you think about it for a minute, how often is the weather dead accurate? Well, not very often unless you live in an area where it doesn't change much. I'm from Pittsburgh, and Pittsburgh, like many other places, they say if you don't like the weather, wait an hour, and you'll like it then. So our weather is constantly changing, which makes it rather demanding to do a weather forecast. But because they're not perfect, does that mean they're not useful? No. There's still a lot of usefulness in looking at a model that is less than perfect. But we do want just enough fidelity to achieve our project objectives. And I think this will come up again later when I talk about how you can, where things go wrong. But one of the places where things often go wrong is number one, not having project objectives. And so it is really important to come out with, reasonable, feasible objectives for what you expect to get out of this phase of the model. And then you want to build that model with just enough details, just enough fidelity, just enough complexity to be able to meet those objectives, but no more. No extra fidelity. You want to minimize the work to keep your models nice and small and fast and easy to develop by only focusing on the problems that you have. Okay, so why do we use simulation at all? Well, objects can influence each other, just like a row of dominoes does. And every system has randomness, breakdowns, illness, late arrivals, materials not showing up on time, all kinds of things like that. Well, the combination of those two is pretty complex. And simulation is uniquely capable of managing that complexity. So in the first section, I talked about some of the traditional uses of simulation is primarily for design and optimization. So this is the sweet spot of discrete event simulation in the design space. And simulation offers unique advantages in these areas. such as being able to understand the system, evaluating alternatives, basically minimizing risk by making your mistakes in the model as opposed to making your mistakes on the real system. In this limited space, most models are purpose-built and often discarded after a single use. But when we created Simio, we saw the opportunity to extend that technology from a one-time use to a tool used on an ongoing basis. And we'll talk about that a little bit more. So beyond a broad application domain, simulation has a number of compelling benefits. Number one, it gives you a visibility in the future. Now, is it a perfect visibility? If it was, I'd be on some Hawaiian island right now, spending my fortune. And no, it's not perfect, but it doesn't have to be perfect to be valuable. And it does give you a window into what is likely to happen. It is a knowledge base to document processes, and this is probably the most underappreciated aspect of simulation. I'm working on a pro bono project now with somebody in the pharmaceutical industry, and they wanted a model, and so we started going through collecting data for the model, and then before I even did a model for them, I gave them a list of like 20 things that they ought to do. 20 basically conclusions from the model. And the reason that I was able to do that is that building a simulation model kind of forces you to ask questions that you might not otherwise ask. It forces you to talk to people that you might not readily talk to. And all of those things can get built into the model, and now you have a knowledge base that documents how things work. And often that model is the first time people have ever seen or really understood how their system works. Because each of the 20 experts knows 5 or 10% of the process, but none of those experts knows even 80 or 90% of the process. But the model does. The model knows 100% of the process. Once you have that knowledge base, you can use it to analyze alternatives, answer what-if questions. Again, make your mistakes early and in the model. I can't tell you how many times we've been called in late into a modeling project, and we say, well, hey, the model tells me that you ought to do X. It is obvious that you ought to do X. You ought to, ditch the conveyor and use an AGV or whatever the case may be. And I can't tell you how many times they've said, well, gee, we already ordered the conveyor. We've already paid for it. We can't cancel it anymore. Where if they had done the model early, they could have seen in that model early that an AGV was a better solution than a conveyor or whatever the case may be. So models give you the opportunity to explore and make mistakes at no cost. It also gives you a way to visualize the process and communicate with each other. If I show, there are some people that relate well to a spreadsheet full of numbers, but I would guess most people don't. But when you look at an animation and see, you can do something like, well, press a button and you'll make machine A fail. And you do that and you see all of the things that happen. You'll see that the downstream machines quickly get starved and the upstream machines quickly get blocked. And you'll say, hey, that is exactly how my process works. Or to the contrary, sometimes you'll see things that happen that should never happen. And even that is a good thing, because now when that operator sees your model, says, hey, that didn't work right, and you change it and make it work right, now he understands the model and he believes in it. So that visualization is one of the compelling benefits. So some of the advantages of simulation is its flexibility. You can model just about anything. The variability, all real systems have variability. so let's consider it. In the visualization, that that 3D animation can be a huge tool for understanding and communication. I've mentioned a little bit before, or I've alluded to it at least, that simulation is used in a lot of different application areas. There are certainly products that exist, like there are products that are designed just for healthcare modeling. There are products that are designed just for traffic modeling. But for the most part, most discrete event simulation products recognize that there is a lot in common, even though it might not seem like it. There's a lot in common between these different application areas. And so you can take discrete event simulation into pretty much any application area. Now, that variation thing that I talked about, a lot of people don't really understand the importance of variation. So I have a simple model here to illustrate how important it is. And normally I give this model as a test in front of a live audience, but consider yourselves lucky that I won't be testing you other than asking you maybe some rhetorical questions. So my system is one of auto detailing. And so I'm thinking of this detailing business where I know I can detail a car in 55 minutes, and I know my cars come in on average 60 minutes apart. And so I think I can make my name, make my business be successful out there by advertising that I guarantee a 2-hour vehicle detailing, and if I can't get it done in 2 hours, it's free. Is this a good business? Is this something that I could do? Well, in order to answer that question, I'd have to say, well, how will this system perform? And just to keep this problem, simple, we're going to just assume that we run 24 hours a day, 7 days a week. So I have a crew of detailers, one on at a time. But so I have, one person is there round the clock to detail these cars, and I want to guarantee 2-hour detailing. So can I make this guarantee without losing my shirt? Well, there's another question that we need to ask, and that is, what is the variability of those two numbers that are on the screen? If those are both constant and my inner arrival time is 0, my inner arrival time is 60 and my service time is always 55 minutes, so every car takes me exactly 55 minutes to detail, what's my average waiting time? And hopefully everybody could look at that and say, oh, well, sure, there's no waiting, because the first car comes in, let's say at 9 o'clock, and the detailer is idle. He takes 55 minutes, so he's done with it at 9:55, gets to take a 5-minute break, and then the next car comes in at 10 o'clock. So that's pretty common. So no waiting time for anybody. My server isn't too badly overwhelmed. He has 5 minutes break every hour. And so sounds like a good model. Okay. What would happen if I made that inner arrival time be variable? So exponential is a common inner arrival time. So what if I made that inner arrival time be 60 minutes? What would that do to my waiting time? So I'll ask everybody to, at least in your mind, take a guess at it. How many minutes or hours do you think the average waiting time would be if I just make that first one be an inner arrival time of 60 exponential inner arrival time of 60 minutes? So again, I haven't changed the average at all. So maybe the first one comes in 9 o'clock, the next one comes in 50 minutes later, the next one comes in 70 minutes later, but on average, they're going to come in 60 minutes apart. So with an exponential inner arrival time and a still a constant 55-minute time, what do we think that's going to be? Anybody think 5 hours? No, it's not at all intuitive, but you can model that either with simulation or queuing theory, and it will tell you that that is the answer. Now, what if I went further and said, well, let's make them both exponential? Now, exponential is a very common inner arrival time. It is not a very common service time, but again, it keeps the problem simple. So if we had exponential distributions for each of those, what would it do? Would it make it better or worse? Would it make it less than 5 hours or more than 5 hours? Again, think about that for a minute. And how many people would think it would be 10 hours? Again, not at all intuitive, but it is accurate. Now, that is so non-intuitive, but it is a very simple system. For those of you, in manufacturing or in the real world in some aspect, do you ever have a system this small? Do you ever have a system this simple? And yet, if we can't predict this one, how can we predict the systems that we use on a daily basis? If you take, and by the way, that can be modeled with a simple source server sync model in Simio, and in fact, we'll do this in one of our later modules. Now, if you take that same thing from a scheduling standpoint, pretty much every scheduling product in the world generates a Gantt chart. And the Gantt chart says, okay, well, I have my first order, starts at this time, it ends at this time where the black symbol is, it's due, or I start paying penalties at this time, and I have this green dashed line as my slack time. And so in this case, it's saying, well, the first one comes in at 9 o'clock, he's done by 9:50, and then I have an hour and a half of, or an hour and 5 minutes of slack time before I have to make it free. So good system. And in fact, pretty much every scheduling product in the world does a deterministic look, which is what this is, constant service time, constant inner arrival time, and tells me that I have 92% utilization and no late orders. So every simulation, every scheduling product in the world would look at this and say, yeah, that's a good system, invest in it. How many people want to invest in it with me? I'm guessing not too many when you actually put in the variability for this and find out that 73% of the time, the orders are going to be more than 95 or 65 minutes late. And so I'm going to be giving away detailing 73% of the time. Now who wants to invest in it? Well, probably not the best place to invest. So if you want to invest in that system, you're going to have to do it on your own. I'm out. Okay, so managing variation is one of the key things that you can often dramatically improve system performance just by reducing variation. So, whenever you get a system, you first want to work to identify variation and explain the variation, eliminate any sources of variation that you can, and often you cannot, but many times you can eliminate or at least explain variation, and that can help a lot. And then whatever variation is left, you need to make sure that you accurately model that variation. So often the degree of variation is much more important than the mean. So if I went back to this problem, if I change the 55 minutes or change the 60 minutes up or down by a few percent, that is probably way less important than getting the variation correct on that. Okay, so I'd like to move on now and talk a little bit about Simio. So we have another half an hour to go through some Simio models. And I want to start by giving a quick overview, and I encourage you, if you haven't done so already, those of you that have Simio installed, you might want to load Simio, preferably on a second screen if you have one, and just kind of look at Simio as I explain some of these things. And I will be going into the software itself later on, but I thought it might be easier just to deal with the the interface in slides for now. So to start with, we have a menu at the top with our files menu, which takes you to different aspects of what you want to do. Then we have the ribbon in here, and the ribbon is context sensitive to what you're looking at and what you want to do. Then underneath the ribbon is the project tabs, and the project tabs correspond to different parts of your model, and I'll explain these in a few minutes. But so we have the facility, processes tab, definitions, data tab, etc. And these tabs will vary depending on the type of object that you're looking at, which brings us to the next thing is over in this upper right corner is the navigation panel. And in the navigation panel, when you first load Simio, you'll see by default, you get shown a model and a model entity, and I'll explain both of those a little bit, but the model is actually the model that I'm building. The current model is highlighted there, or the current object that I'm looking at is highlighted. Just below that navigation window is the properties window, which shows the properties of whatever object that you have currently selected. And then in the center here is my facility view, which is where I will be building my model of the facility. So in the facility view is basically anything that you might look around and see in your real facility. And I try to use generic words like facility as opposed to plant, because facility could be my supply chain, it could be my hospital, it could be a grocery store, it could be a production plant, it could be a shipping yard, anything you want, but any of those would be your facility, which belongs in the center window. And then finally on the left is the libraries, and there's actually two different libraries there, but the libraries, and these are the low-level components that you can use to bring into Simio. And I'll describe each of these in more detail. Before I get back to that, let's talk about some general object concepts. So the first thing is we have the concept of objects and models and projects. So an object is something that defines data, logic, behavior, view, events, interaction with other objects. So basically what that means is these are complex objects. Some other products have very simple things. Sometimes they're called modules or other things. But in Simio, we call these objects because they do conform to the programming definition of objects, but probably more important than that, these are complex things. So like it could be a machine, but a machine isn't simply a machine that is busy or not. Machines have lots of data. They have interactions with other objects. They have setup times. They have secondary operators. They have failures. They have costing. All of those types of things are included in the object. Now, in Simio, a model is simply an object that is executable. So there is really no difference between a model and an object in Simio. A project is simply a collection of models, objects, and there is basically no difference in Simio between a project and a library. Properties, states, and events are all characteristics of an object. The inputs to an object, I guess the key difference is properties are static and states are changeable during a run. And we'll come back and talk about all of these things in more detail. And then resource entities and transporters are all types of objects that constrain flow through the system or enable flow through the system. Okay. Before I go any farther into the constructs, I want to just introduce a couple high-level constructs that basically translate into those tabs that are across the top of the facility window. And one of those tabs is called the Processes tab. And the process is where I can put in a set of actions that take place over time. And at the bottom, you can see a very simple process is I want to seize a resource, I want to delay by some process time, and then I want to release the resource. And processes are used to add uh, or to deal with more complex situations, custom logic. One of the nice things about our objects is they are very comprehensive, and they do most things that you might want to do is automatically built into the object. But no matter how much we put in the object, I guarantee you there will be something that your facility requires that we didn't think of or just decided not to put in. When that happens, what do? Well, in some products, you're just stuck. You just have to say, well, that's what the object does. Approximate your system as best you can. In other products, maybe you need to go to a programming solution that you get out your Visual Basic or your C++ or a custom language, and you go start programming the object. And you can do that in Simio as well, but almost nobody does because we also have a patented capability called add-on processes that basically allows you to graphically customize an object with any additional logic that you want. And we'll discuss that a little bit later on. We're not going to go too much into processes in this workshop. That's a little bit beyond the scope of this workshop. But I wanted to let you know that it's there. And that is what allows you, that gives you the flexibility to model just about anything you would want to model. Okay. Another one of the tabs at the top of the facility window is the data tab. And this is where our data is represented. In Simio, models just in general have large amounts of data. As I mentioned, it wasn't too many years ago when a model that exceeded 1 megabyte would be considered a very large model. Now, for those of you who attended the first session, I told you yesterday we had one of our customers was complaining about a model that ran slow, and it contained 29 gigabytes of data in this model. And that is huge. And how do we handle things like that? Well, we handle those with data tables. That basically Simio has the ability to represent pretty much any data you want in model. At its simplest level, it looks kind of like a spreadsheet, but they can be relational tables, and the schema or the design of that table is something that you do, not us. So we don't put any constraints on how a table is designed. So if you want a table to exactly match your external data to facilitate import and export, you can do that. If you want to transform your external data into something that is a smaller subset and easier to use in Simio, you can do that as well. But the fact that it's user-defined is significant. The other thing is we have very flexible import and export that supports many common data forms, databases. So you can see from this diagram here, I can say I want to make a binding from a table to a database, and then what kind of database do I want to go to, or a CSV file, or an Excel file, or a Wonderware or Viva MES system, or an XML transformation, and more. If none of these works for you exactly, you can also go to our API, and our API for all of these is included with the software. The source code that was used to create a MySQL database access is included with the software. And so if you said, well, I have a SQL database that is somewhat similar to the MySQL, but different in some way, maybe I have two levels of passwords or something like that, you can just start with our source code, change change it and match your source code. So basically, you can import just about anything that you would want to import and export. Okay, so going back into our standard library, so that was the library down the left-hand side of the window. And again, this is just a quick overview of what is there. So we have the source and sink, and that's the terminology we use to bring entities into the system and out of the system. Entities is the generic term we use for the things that are moving around in the system. So that could be people, it could be parts, it could be cars, it could be cups of coffee, it could be pills, anything you want can be the entities. And so the source and sink are how we create and destroy those entities. Server, combiner, and separator are three of the what we call fixed objects that stay in one place and kind of allow flow through them. And we'll talk in some detail about the server. Resource, vehicle, and worker are more dynamic objects that can move around. They also can serve as constraints for either transporting, carrying, or working on other parts. The nodes and the connector or links are interrelated. The nodes are basically the endpoints of links, and we have 4 different types of links in the standard library. Connectors, which happen a 0 travel time. Path is what you'll use most often, that allows entities to move at their own speeds. Time path allows travel in a specified time, and conveyor allows movement in a conveyor-like format. Now, I know I'm giving you a very quick introduction to all of these. Actually, I'm just about to convert over to looking at the software, and hopefully much of this will become clearer. And again, you can feel free to play around with these things if you have the software in front of you as I talk. Okay, so building a sample model, we're going to build a simple model. And this simple model is going to be a simple flow line where entities are introduced at a source. They go through a server, server 1, and then flow to a server 2, and then flow to the sink where they leave the system. So it's a small system, and we're going to go through and build this and then come back and experiment with it some. So let me bring up software. Okay, so if you have been playing around with the software and it doesn't look like this big open screen, then I encourage you to do a file new, so file new, and then you'll get back to this open screen. And so what I'm going to do in here is do a drag and drop. So I'm going to click on source and drag it in and let it go. And that becomes my first, where my entities come into the system. I also want to show you another interface is a multi-place interface. If I double click on server, so I'm going to click twice on that, I can bring it in and click to drag it once, and note that I still got the crosshairs. And so I can drop as many servers as I want to drop here. So I clicked again. When I'm done dropping servers, I hit the right click or escape, and that takes me out of that multi-place mode. And then the last thing I'm going to do is click on the sink and drag and drop a sink over here. So hopefully everybody's with me. I just did a single click on source, dropped it in, a single click on sink to drop in the one over here, double click on server, dropped one, dropped a second one, and then escape or right click to get out of that. So that's my source server sink. And even now, if I come up and hit the run button on the run tab, if I hit the run button, I've got a model that's running. And so you'll see the green triangles are the entities that are moving through the system. And there are some defaults that are taking place now. So, and we'll go into a lot of those properties as we go. but the default says, hey, when I leave this blue exit node, it's going to look for the nearest entrance node, and so it goes there automatically. From here, it waits in the input buffer here until there is server capacity available here. This represents the entity that is currently being served. The green color of the server represents the state of being busy or idle, and others. And then it moves on to the next one, repeats that, moves to the server, and then is disposed at the server. So I just hit the stop button up here to indicate that I want to stop that run. By the way, I'll mention this ahead of time, and it will probably come up that at some point, let me just fast forward here to show you what system you will probably get to this point at some point, and then you're going to say, okay, well, I want to change something about the server. And you'll see that it's all grayed out and I can't change anything there. Well, I can't change anything because I am still in run mode. And you can tell that in many ways. Sometimes you'll see the green triangles on the screen, but always when you're in run mode, you'll see the stop button up here is lit up. So to get out of run mode, I need to click that stop button. And then at that point, I can go over here and change things in the properties window. Okay, so let's continue enhancing our model here. And I'm going to say double click on path. So remember what a double click does, puts me in multi-place mode. So when I double click on path, when I'm going to place a path, and when I place a path, that's actually a hard thing to say, place a path. It's important, the direction is important. So I want to go from the output node, which is blue, to an input node, which is gray. So I'm going to click on the output node, click on the input node. Now, you'll note that I'm still in multi-place mode. That crosshairs indicates that I'm ready to do another one. So I can do another one here and another one here. So I've done 3 paths in here. And at this point, you want to hit the escape or right click to get out of this multi-place mode. But since it will almost undoubtedly happen to everybody, because it happens to me frequently, if I don't hit that and I say, oh, well, now I want to place another server. As soon as I go back here to place another server, what's happening on my screen? Well, it thinks it's trying to be helpful by thinking that I want to place a path over here. And so whatever direction I'm going off screen in, it's scrolling me automatically in that direction. So, you can often get kind of lost in that. So when that happens, again, you can hit escape or right click, and then go up to the view ribbon and say view all, and it brings you back to your home screen. So if that happens, you'll know how to get back again. So get out of the multi-replace mode and then go to the view window to get back here. One other thing that we might do while we're here is bring in a model entity. So you'll note that there was an entity in here, and that uses the default entity, which is fine if you don't want to change anything. But if I wanted to change anything about that, then I would want to drag the entity in from down here in the project library. And so now I have dragged a default entity in. Let's do one more thing while we're here and say, well, let's click on server 2 and go up here to the status pi button. And we're not going to click status pi. What we're going to do is click the arrow next to status pi and use a quick create feature on resource state. And so what this does is creates a pie chart for you that is already hooked up to the server. So by clicking upper left and then clicking the lower right, I've created a pie chart. And I generally, oh, I think it's already done there. Okay. So, and that pie chart, shows you, the potential states. So I'm going to zoom in on that just so we can see what different states are supported. So these are all the states that are built into the server. You can put in your own custom states beyond this, but It has starved, which is idle, processing or busy, has blocked, which means I've got something there that can't leave, a failed state, off shift, and other more detailed states. So if I run the model now, go back to the run ribbon and press run, or you could have gone directly to this speed key up here. If I hit the run ribbon, you'll see that this is showing idle now, and now it's showing busy. So there's my pie chart that's showing a real-time update of what server 2 is doing. Okay. All right. I can see that I have gotten well behind schedule on here. So let me skip back to the slide again and talk about dot notation. And normally I would spend some time showing you this, but in this case, I'll just take the short version of it. Is the because objects can be defined of other objects and have other objects and other fields related to it, to deal with that in an object-oriented environment, we usually use an x.y, where y is a component of x. So this is an example. In our model, we had something called server 1, and it has a capacity keyword in it, and part of that capacity is allocated, and one aspect of allocated capacity is average. So you have to build these from left to right, but in fact, it's easiest to read from right to left, and so this expression would represent average allocated capacity of server 1. And so we have object properties that we can specify here. And this is what the expression editor looks like. So again, I have to take the abbreviated version, and I'll leave it to you to read this. But to open up the expression editor, you simply press the down arrow on the right-hand side, and it'll bring up expressions, support of the expressions. Okay, so what can those expressions be? Well, there's lots of different things that they can be. And although there are lots of choices, this slide is a slide that you might want to note to come back to later when you get the slide pack. And you can see that there's a random, which has lots of choices, and I'll go into that in a minute. There's math with lots of choices, which we're not going to cover in this. Also, there's date time with lots of choices. But the things that you're most commonly going to use is something like an object name, like server 1, dot capacity keyword, and then things like scheduled utilization. So if I wanted to find what is the utilization of server 1, I would do server 1 dot capacity dot scheduled utilization. If I want to find the number of entities, the current contents of the input buffer of server 1, I'd do server 1 dot input buffer dot contents. So you can see how this would work. Some commonly used expressions, the most commonly ones, so like the expression that we used in our our variability example was a random exponential distribution, which takes a mean. The exponential distribution looks kind of like this. Triangular distribution is also very common. Looks like this. And a uniform distribution is also very common, kind of looks like that. While it is commonly known, the normal distribution isn't so commonly used because a lot of people don't often understand it as well as they think it is. In fact, because it's unbounded, a normal distribution can produce negative values. So what does it mean if I say I have a normally distributed time with a mean of 5 minutes and a standard deviation of 3 minutes, and it happens to generate a sample of -2 minutes for processing time. What do I do with a -2 minutes of processing time? So unless you can deal with things like that, you're better off staying with something like a triangular distribution. Okay, so we're going to take our simple flow line and add some of these capabilities to it. So let's go back into my model and say for my inter-arrival time, I want the random exponential distribution to be 2.4 instead of 2.25. And I'll show you several different ways of doing that. One is that you can just overtype in here. So I can do a 2.4 directly in here. So there's my new distribution. So you can see the whole thing. Let's go into server 1 and there say we want there the distribution to be a random exponential 2. So again, I could just type in here. I could overtype that with an exponential 2, or I can do the pull down list. So I just hit that arrow to the right hand side. I can backspace, well, let me do it from the beginning. So I can hit R. It takes me to the first R in the list, which it's a little bit hard to see on the screen, but it is highlighted random. And so I can type RANDOM if I want, or I can just hit dot and it accepts random and takes me to the rest of the list. Under the rest of the list, then I can, look at any one of these. I can hover over it, so it tells me, what that distribution is used for, what the properties are used for, or in this case, I wanted exponential, so I hit E and it takes me to the first E in the list, which in this case is Erlang, not what I want. So I'm going to go down 1 to exponential and hit enter, and there's my random exponential mean. And so in this case, I can double click on mean and say I want a value of 2. Okay, if you didn't catch that, I'm going to do it again on server 2. So on server 2, I clicked on server 2, go over to the properties window, processing time, use the pull down list. And in this case, I'm just going to backspace over the first part, hit a dot at the end of the random, brings up my exponential. Here, I'm just going to use, instead of the speed keys, I'm just going to use the cursor key. And I cursored down about 6. That took me to the exponential mean and hit enter. And again, the mean of this one, we want to be 1.71. Okay, so quick review. I have my source being random exponential 2.4, server being random exponential 2, server 2 being random exponential 1.71. And so I can run that model. And I think we need to go up here to my to my run window, in my run window. And let's set the speed factor to something higher, like 20. So now I can see things moving through the system fairly quickly. And in fact, if I want, I can run that fast forward and run fast forward to the end. At this point, I can go over to my results window. So up here in the tab, in the results window. And I'm going to minimize this window over here so we can see better. But in my results window, that tells me, everything that I need to know about that model. So you can see it is presented in a pivot grid table. And so I can see, for example, what is my average number in system was 7.1. The average time in system was 0.28 hours. And if I wanted to, I could change that to other units. If I wanted to go down and look at my server, I could say, well, my server scheduled utilization is 84% on server 1 and 71% on server 2. Okay, so So we've looked at our pivot table here. Now let's take a look at randomness to start with. Well, did everybody have the same answer? Did everybody have the answer of 0.183? Oh, let's go back to the top here. 0.2893 for average time in system. I'm guessing probably not. So let's look for a minute, and I apologize, I'm going just a little bit over, but I'm almost done here. What is the value of a single trial? Which is what we just did. We did one single trial. With a single trial, if I, let's say, I don't know how many of you live in states that that allow gambling. They've allowed gambling in Pennsylvania fairly recently, being one of the conservative states we get last for things like this. But they do have a casino down in Pittsburgh, a few miles from my house. And so maybe I want to go down to there, and I've heard there's this game called craps, where rolling a 7 is a good thing. So I say, well, I'd certainly like to double my retirement savings. So what if I take a pair of dice and I roll the dice and I get a 7? I say, oh, cool, this game's easy. And so I go down there and bet my life savings on a roll of 7. Is that a good thing? Well, I'm guessing not, based on research of 1. What if I rolled my dice 10 times and got a 7 9 out of 10 times? And I'd say, well, that's all. That gives me more confidence. Not really high confidence enough to bet my life savings. What if I, rolled it 100 times and got a 7 90 times out of 100? Well, now I'm starting to feel more confident. What if I rolled it 1,000 times and got 900? Okay, well, at that point, I'm thinking 2 things. Well, I'm not going to bet all my life savings on one roll, but maybe I do it in 10 rolls, and 9 out of 10 times on average, I'm going to win. The other thing that I take away from that is I'm going to want to take those dice with me. Right? So maybe the casino might not like it, but I like a pair of dice that's going to roll 7s 90% of the time. So if you're not confident betting your life savings on one roll of the dice, how confident are you at making a model recommendation based on one replication? And I would say that interactive results based on a single replication are generally not actionable. Okay, so I will end here now. And again, I think we now have a 10-minute break scheduled. If we can cut that down to maybe 7 minutes, enough time to go refresh your coffee or get rid of some coffee. And then we'll restart just a couple minutes late off our schedule. So thank you, everybody, and I'll see you in 7 minutes.